35 kilometers north of the village of Saint-Paul-l'Estorance, in the Cataract region of southern France. One of the most complex engineering projects in human history is being assembled. It is called ITER, an acronym for International Thermonuclear Experimental Reactor, and it represents the collaborative effort of 35 nations, including the United States, the European Union, China, Russia, India, Japan, and South Korea. It is the largest scientific experiment ever undertaken in terms of the number of nations involved, the complexity of the engineering, and the stakes of what success would mean. ITER is attempting to demonstrate, for the first time at significant scale, that nuclear fusion, the process that powers the sun and every star in the universe, can be sustained in a controlled way here on Earth, producing more energy than is required to maintain it. If it works, it will be the beginning of the end of the energy problem that has constrained human civilization since the Industrial Revolution began. To understand what ITER is attempting, you first need to understand the fundamental physics of fusion. The sun generates energy through the fusion of hydrogen nuclei under the extreme pressure and temperature at the sun's core, approximately 15 million degrees Celsius. Hydrogen nuclei move fast enough and are compressed closely enough together that they collide with sufficient energy to overcome their mutual electromagnetic repulsion. When they fuse, they form helium. In the process, a tiny amount of mass is converted directly into energy, according to Einstein's famous relationship between mass and energy. The energy released by fusion per unit of fuel is almost unimaginably large. 1 kilogram of fusion fuel releases approximately 3 times 10 to the power of 14 joules of energy, roughly equivalent to the energy released by burning 10 million kilograms of coal. The primary fuel for the type of fusion ITER is testing is a combination of 2 heavy isotopes of hydrogen, deuterium, which can be extracted from ordinary seawater, and tritium, which is bred from lithium. Deuterium is essentially unlimited. Lithium, while finite, exists in quantities sufficient for thousands of years of fusion energy production at civilization scale. Fusión produces no carbon dioxide. It produces no long-lived radioactive waste. The neutrons produced activate the reactor structure, but the resulting materials have radioactive half-lives of decades rather than thousands of years. Fusion fuel cannot melt down. The plasma is so difficult to sustain that any disturbance causes it to collapse instantly, terminating the reaction. It is not possible to build a fusion bomb from a fusion power plant. The challenge is not the fuel or the physics. The challenge is the container. Achieving fusion on Earth requires replicating, in a machine built by human hands, the conditions that exist at the core of a star. The temperature required for the deuterium-tritium fusion reaction ITER uses is approximately 150 million degrees Celsius, 10 times hotter than the core of the sun itself. No material on Earth can contain a plasma at 150 million degrees. Nothing. There is no metal, no ceramic, no composite that can survive contact with material at this temperature. The plasma would vaporize any physical container instantaneously. The solution the physics community settled on, after decades of research, is magnetic confinement. Plasma, which is a state of matter in which electrons have been stripped from atomic nuclei, leaving a gas of charged particles, responds to magnetic fields. Specifically, charged particles in a magnetic field spiral along the field lines rather than moving freely in all directions. If you can configure a magnetic field in the right geometry, you can keep the plasma suspended in the center of a chamber, never touching the walls. The geometry that has proven most effective is called a tokamak, a Russian acronym coined in the 1950s, reflecting the Soviet origins of the concept. A tokamak is a toroidal, donut-shaped chamber surrounded by a complex arrangement of superconducting magnets. The magnetic field lines run in helical patterns around the inside of the torus, creating a magnetic bottle that holds the plasma in suspension, compressed and heated, without allowing it to contact the walls. ITER's magnetic field is generated by superconducting magnets operating at negative 269 degrees Celsius, colder than the surface of Pluto, for degrees above absolute zero. These magnets will produce magnetic fields 18 times stronger than those generated by the magnets used in MRI machines, which are themselves considered among the most powerful magnets in routine human use. The engineering challenge, stated plainly, is to build a machine that simultaneously maintains the coldest, large-scale environment on Earth and the hottest, with a gap between them, measured in meters, bridged by magnetic fields. The scale of the machine being built at Cataract is staggering by any measure. The ITER tokamak will weigh approximately 23,000 metric tons, roughly 3 times the weight of the Eiffel Tower. The central magnet system alone, a stack of 6 superconducting coils that runs through the center of the machine, weighs 1,000 tons and will generate a magnetic force equivalent to the weight of approximately 900 fully loaded Boeing 747 aircraft. The machine sits in a seismic isolation system, a cradle of 900 pads designed to absorb ground motion from earthquakes, because even minor ground movement during plasma operations could disrupt the magnetic field geometry. The superconducting cable that winds through the magnet coils contains niobium tin filaments thinner than a human hair. The total length of superconducting strand in the ITER magnets is approximately 100,000 kilometers, roughly enough to wrap around the Earth 2.5 times. The vacuum vessel, the toroidal chamber where the plasma will actually burn, must maintain a vacuum 100 times lower than the atmospheric pressure on the surface of Mars. It is simultaneously one of the largest high-vacuum environments ever created and must withstand the neutron bombardment from fusion reactions without the structural integrity of its walls being compromised. The manufacturing of ITER components has been distributed across the participating nations, each contributing major components according to their technical specialization. Components manufactured in Korea, Japan, Russia, the European Union, the United States, China, and India must fit together with millimeter-level precision when assembled in France. ITER is not a power plant. This point is important and frequently misunderstood. ITER is designed to demonstrate scientific and engineering feasibility at scale. Its target is to produce 10 times more thermal energy from fusion reactions than the energy input required to heat and sustain the plasma, a ratio called Q of 10. No previous fusion experiment has achieved a Q greater than approximately 0.7. ITER aims to reach Q of 10 and sustain that ratio for pulse durations of several hundred seconds. The step after ITER is a demonstration power plant, currently being designed under the name Demonstration Power Station, that would take the ITER design and add the components necessary to actually generate electricity and feed it to a grid. If ITER operates as designed, and if DEMO is subsequently built, the first commercial fusion power plants might potentially begin operation in the second half of this century. This timeline is long. It has also, historically, been longer than optimists predicted at each previous stage of fusion research. The common joke in the field, fusion is 30 years away and always will be, reflects genuine frustration with decades of scientific progress that is not yet translated into commercial energy. But the honest answer is that the physics is not the problem. The physics is understood. The engineering challenges are severe but not intractable. They're challenges of precision, material science, and manufacturing, not of fundamental unknowns. ITER represents, for the first time, an experiment scaled large enough to actually test whether the engineering can be made to work at the level required for useful energy production. The nations involved in ITER have, collectively, committed approximately 22 billion euros to the project over its full construction, operation, and decommissioning lifecycle. This makes it one of the most expensive scientific projects in history, surpassed only by projects like the International Space Station and the Large Hadron Collider. The geopolitical dimension of the collaboration is not incidental to the project's significance. China, Russia, and the United States are jointly building a machine in France, sharing scientific data and technical expertise in pursuit of a goal, clean, abundant energy, that is so fundamental to human welfare that it has produced genuine cooperation among nations that are, in most other domains, engaged in intense strategic competition. The ITER agreement has survived significant geopolitical disruptions that might have been expected to derail it. There is something worth noticing in this. The project has survived because all participating nations recognize that the potential payoff, a functioning fusion energy demonstration, is worth maintaining even under conditions of broader geopolitical tension. Energy security is a national interest for every nation on Earth, and fusion promises energy security of a kind that no other technology currently visible on the horizon can match. The machine being built at Cataract will, if it achieves its design targets, produce a plasma hotter than the center of the sun inside a chamber that fits within a building. It will maintain the laws of stellar physics inside a structure built by human hands, from materials mined from the Earth's crust, using knowledge accumulated across a century of plasma physics research. It is the most ambitious engineering project in human history. And it is not science fiction. The components are being machined, shipped, and assembled right now.